Should we get started, Brianna?
Yes, please start when you're ready.
That
And
is
then
right.
we'll just ask all to, if you could all mute yourselves, that would be great. And then we will have all of the courses recorded, and then we will make those available as well. And then Spyros, I'll turn it over to you.
Thank you, Brianna, and thank you all for attending. So quantum systems information entanglement is a short course that was designed for students and for anyone who wants to learn the basics of quantum information and in particular quantum communication. So this course is hosted by the Center for Quantum Networks. This is a big collaboration among a lot of universities and research groups. And I encourage you to visit our webpage and check out the research. I think there are also some open positions for postdocs. And I also include the email in case you want to reach out and have any questions. I think Brianna will text those information in the chat. All right, so this course will be divided into 3 lectures. Today we'll talk about basic principles of quantum systems. Next week, we'll get into applications, in particular to quantum teleportation. We'll see how the non-classical property of entanglement is helpful to achieve those type of applications. We'll try also to interpret it. And finally, we will conclude this lecture with talking about decoherence, meaning the phenomenon where noise is interfering with our system, and we'll see how we can tackle it in order to have applications, broad scale applications like quantum networks. So today I'll start off with some introduction regarding why do we even need quantum mechanics, why classical mechanics, when classical mechanics fails to provides intuition of what's exactly happening in the experiments. And before I get into quantum mechanics and describe it, I will briefly review classical systems and their basic principles in order to have some frame of reference, some context in order to extend it further. The basic principles that I will talk about will be the quantum observables, quantum states, and the evolution of them. And I will conclude today's lecture with talking about briefly on how to encode information, those quantum systems. All right, without further ado, let's start with the introduction and talk about the Mach-Zehnder interferometer. Let's assume that we have single photons sent through the Mach-Zehnder interferometer, and then we detect them. So the Mach-Zehnder interferometer is constructed with 2 mirrors and 2 beam splitters. Mirrors, as always, just reflect the light. Beam splitters are devices which, if we were talking about classical light, thermal light, then what would happen is that the beam will be split into 2 beams. But when we are talking about single photons, then a beam splitter just allows the photon to go in one or the other path with some probability. So I have here the red and the blue path. And we can consider here a balanced beam splitter, meaning that the probability to take its path is just 1/2. Also, we want to take into account the possibility that the photon will travel in different lengths between the upper and lower paths. So we can introduce a phase shift. Here we introduce it in the upper path, and then we have a detector. All right, so given that information, here is the problem. Here's the what we're interested in. Let us assume that we want to send single photons single photons one at a time through the Mach-Zehnder interferometer. So based on what we said so far, what we expect to happen is that half of them will go through the upper path and the other half will go through the lower path. Now, the ones that went through the upper path, they will find the second beam splitter and then we'll split again. Half of them will be detected and the other half will be discarded. And from the ones that went through the lower path, again, half of them will be detected and half of them will be discarded. So in total, in that scenario, we would expect to detect half of the photons that we sent through. However, that is, okay, so practically that means that the phase shift that we introduced plays no role. But that is not what we end up counting. So the photons that we count falls within this interference pattern, which is really weird. Let me mention that the interference pattern is known through classical optics. However, in classical optics, we have a wave, we have an ensemble of particles. And when we send light through the beam splitter, then the phase shift actually is expected to play a role, because during the second beam splitter, we would expect to see some interference and some destructive or constructive interference. And that would take into account the result that we might end up measuring, detecting all the photons on none of it. But when we have single photons, and may I repeat that the single photons are sent one at a time, then the phase shift playing a role is pretty weird, because it seems like the single photons interfering with themselves. This is what we also sometimes call wave-particle duality, because at least the observation is that the particle behaves as if it was a wave. So that's how classical intuition fails, at least in that situation. So we need to come up with a new theory that has a structure, a mathematical structure that can take into account those phenomena and explain them. And that is quantum theory. So let me first off, let's start off with classical system and present some principles in order to extend them later. So the first one is that a property, a classical property, is always represented by a real valued number. That could be position, that could be the momentum, the charge, the mass, anything. This is a really fundamental postulate. It's taken so for granted that textbooks sometimes don't even mention it, because we all assume that property will always, in the end of the day, be some number, some real number. The second principle is that a system, a physical system, and classical mechanics can be represented by a point in the phase space. Phase space is something that appears in Hamiltonian and Lagrangian mechanics, not that much in Newtonian. The point here is that if we have a system that can be fully described by position and momentum, then we can take this point in this phase in the coordinate space and call it the state of the system. That practically encodes all the information that we care about. And finally, regarding evolution, the evolution of either the property individually or the state in total is deterministic. By deterministic, we mean that there is a differential equation that governs that evolution. So if we have a property, then the differential equation of this property over time will give us, given the initial conditions, and this differential equation can always predict where the point will end up being in the phase space. And that is practically a clear trajectory. Here on the right of the phase space, I have the differential equation for the position and the momentum. The first one is practically the definition of momentum, and the second is the Newton's first law. All right, so moving on, before I get into quantum, let me also introduce Dirac notation, because it's going to be really helpful. And anyone who wants to start doing research on quantum information or want to read textbooks or papers should familiarize themselves with Dirac notation, because you will see it's going to be pretty useful. So in this Dirac notation, when we have a column vector, we're represented by ket. Ket is this symbol, so we have the vector x, so it's just this x between the vertical and the right angle line. And the row vector is represented with the symbol that we call bra. You will understand in a second why Paul Dirac gave those names. We can always go back and forth from a ket to bra, from a column vector to a row vector with an operation which is called conjugate transpose. Practically, that is transforming the column into a row or vice versa, and we apply also conjugation. So using Dirac notation, the inner product can be represented by a bra followed by a ket. So we have in total a bracket. And of course, an inner product is always a scalar value. And we also have the outer product, which is a ket followed by a bra. And then that gives us a matrix. And here's an example of how Dirac notation is actually useful. So if we have a matrix represented by this outer product multiplied by a vector, then we can always rearrange it and have the vector multiplied by this inner product that can go in front, and we have that's a coefficient multiplied by this vector. So as you can see, regarding calculations, Dirac notation is really, really useful. And finally, throughout this lecture, we will be using an orthonormal basis that we call computational. Is just names that we give to those two orthogonal vectors, 0 and 1. And since that resembles the bit, that's why we call it computational. All right, so let's move to quantum mechanics and to the first principle, which is the quantum properties. What is a quantum property? What is a quantum observable? Okay, we've already seen that a classical property is represented by a number. Now, in quantum mechanics, a quantum property, known as a quantum observable, is represented by a matrix. And this is the first big difference between the two theories. So matrices always have eigenvalues, and if we impose that those quantum properties are represented by matrices which have real eigenvalues, or in other words, we call those matrices Hermitian matrices, then those eigenvalues can actually represent the possible outcomes of the measurements that we perform. That might sound confusing. Let's give an example to clear things up. Let us assume that as a property now we have the photon detection. The photon detection is a binary property, meaning that in this detector that we talked about before in the Mach-Zehnder interferometer, we will have two possible cases. We either measure the photon or not. So this property we can represent with this outer product of the vector 0, which will give us this matrix. This is a diagonal matrix, and as it's kind of obvious, I hope to everyone that the eigenvalues are just 0 and 1. And so we can associate the eigenvalue 1 with the detection of the photon, and we can associate the non-detection with the eigenvalue of 0. Of course, we can do the same for another detector that is in the other path of the Mach-Zehnder interferometer. Here we have another outer product of the vector 1, a different matrix, and again, the same eigenvalues that we can associate with the same events. Now we can go a step further and consider a quantum property that takes into account detection for either one or the other detector. It's a more universal one. So this is another Hermitian matrix. I'm calling it here D, which has two possible outcomes, lambda 0 and lambda 1. The only condition here is those two numbers should be different, so we can differentiate on whether the photon went to one detector or the other. And if we assume numbers to be like 1 and -1, then we end up with this matrix that corresponds to the detection of a photon. And you might have seen this matrix before because it's, of course, the third Pauli matrix, sometimes called sigma Z or Z. Photon detection is not the only property that we can describe in these terms. For example, we could have the polarization. Polarization could be orthogonal or vertical, and then let us assume that we apply a filter, a vertically polarized filter, and then at the end we only get the vertically polarized light, and that would be again the same matrix, now calling it pi 0. If we had measured the horizontal polarization, we would have a different matrix, and then again we can combine them all together and we can associate the polarization of the photon with this matrix, again the third Pauli matrix. There are different types of observables, And we already seen that when observables, when properties have only two possible values, then they can be represented by two-dimensional vectors. We already seen photon detection. We've seen photon polarization, but those properties could be, for example, the spin of the electron. It could be the flow of the current, meaning it can be clockwise or anti-clockwise. However, we could have also properties that have more than two possible values. Those properties would be represented by finite dimensional matrices. For example, the electron excitation is one of those properties, or we could decide to measure how many particles we have, for example, how many photons in a mode. But of course, we can have continuous variables. We can have properties that have infinite possible values associated with infinite dimensional vectors. For example, the position of a particle is such a property, or the momentum of a particle. We could have the amplitude of a wave or the phase of the wave. So more or less, this is what I want to mention about observables and how we can have this type of language to incorporate any possible property that we can think of and have this mathematical structure. Before I move on to quantum states, do we have any questions regarding observables? If not, I will continue and maybe I can leave some time up at the end. All right, so regarding quantum states, we've already seen that classical systems are represented with points in the phase space. Now, we cannot do the same thing in quantum mechanics, and the reason is the uncertainty principle. Here I have the uncertainty principle for position and momentum. It's called the Heisenberg uncertainty principle, and we see that the variance of position times the variance of momentum is lower bounded by a number. This h bar is, of course, the Planck's constant, meaning that we cannot simultaneously measure position and momentum with arbitrary precision. That graphically implies that in the phase space, if we were to measure position and momentum, like similarly to the classical case, we would end up to this uncertainty disk, this area where we can imagine that the particle is somewhere around there with some probabilities, but we don't know exactly what it is. As you can imagine, there might be different cases, different systems which have similar uncertainty areas. So we have to come up with a more sophisticated way to represent quantum systems. And one way to do that is by functions. We can have 3D functions in the phase space. Here I have picked the Wigner function, but there are a lot of different functions that can do the job. For example, you might have heard the P function or the Q function. There's actually a family of those that, depending on what is the situation, we pick one of them. I picked Wigner because it's the most popular one. On the left-hand side, I have the Wigner function of the vacuum, meaning we have no photon. And on the right-hand side, we have the Wigner function of two photons. As you can see, the Wigner function can be even negative, can also be singular. And those negativities and singularities sometimes indicate interesting phenomena in quantum mechanics, but I don't have time to talk about them now. Let us also see exactly what we mean by Wigner function. Let's give the actual expression. So we have Wigner function given by this, and let us break that down into pieces. So we have Q, which is just the outcome of position observable. We have P, which is the outcome of the momentum observable. X is just an auxiliary variable here, just we use it to calculate the integral. And finally, we have this outer product of the vector psi. And this is what we call in quantum mechanics the quantum state. So in other words, any quantum system can be represented fully by its Wigner function, or we could also represent it with a quantum state, which is just a vector. It depends on the case. Sometimes for continuous variables like position momentum, it's easier to work with the function. Sometimes with lower dimensional systems, we prefer to work with the vectors. Those two things are complementary. Also, I picked continuous variables. I picked position and momentum just because I want to draw this analogy between classical and quantum systems and show what is the difference. However, we can have a Wigner function for any type of quantum state, regardless of if it's continuous or discrete. For example, here I have the Wigner function for a system that is governed by properties that can take binary values. It's a bit more complicated mathematically because here it's different. We use a different way to construct the phase space. We use those operators A, which depend on the Pauli matrices. That's beside the point. The point here is that any quantum system can be represented with a Wigner function or a quantum state. And a quantum state is a vector. So let us see what mathematically that implies. So if we have a vector as a quantum state, it means that this vector can be written as a superposition. That means that if we have a vector psi, we can have a basis, the computational basis that I mentioned before, and we can project these states onto 0 or 1. And since we already defined quantum states to be vectors, that means that the vector 0 and the vector 1 are also quantum states. And that is pretty interesting because using that mathematical language, we can fully describe the phenomenon that I talked to you in the first slide regarding the Mach-Zehnder interferometer, meaning that we can associate the case where the photon is at this red path of the interferometer with a state 0, and this will be the state that will be detected in that detector. We can associate the quantum state for a photon that goes through the blue path and detect it with a D1 detector. But before the actual detection, the whole system can be represented as a superposition between 0 and 1. Also, in order to keep some consistency, we don't consider every possible vector. We define quantum states as vectors that are normalized. That practically means that they have a certain length equal to 1. And if we impose that condition, that implies that those coefficients in the superposition A and B will be connected through this identity. So a squared plus b squared should be equal to 1. Now, in mathematics, whenever we see a sum of numbers, of positive numbers to sum up to 1, that of course always resembles a probability distribution. And as we will see, though this probability distribution is actually related to the probability that we'll end up measuring the photon in one or the other detector, meaning that with probability a squared, we're going to measure the photon in the D0 detector, and with probability b squared, we're going to measure the photon in the other detector. And of course, we can describe using the same language different other situations. Again, if we go back to the case of the polarized photon, we can assume that here we have a superposition of the two orthogonal polarizations. But what's happening after the measurement is something that I also want to put some attention on. So in order to keep things consistent, we need to create states for associate the system to states after the measurement has been performed. We already talked about those observables that correspond to matrices. Let's here assume that those matrices are the horizontal and the vertical polarizers. And the state after the measurement, meaning after it passed through the polarizer, will be this matrix multiplied by the vector and divided by the square root of pi. Pi is just related with a probability of that happening. So for one case, we have probability A squared for the state to end up being in the vertical polarization, and with probability B squared to be in the horizontal. Also in physics, we call that phenomenon, this situation, the collapse of the states. You might have also heard collapse of the wave function. That is what this term is referred to. And let me also, okay, and yeah, those are two examples for quantum states, but again, we can have different scenarios where are also, they also correspond to quantum states. For example, we can have the quantum state for the spin of the electron. We could have a quantum state representing the excitation of the electron. We could have a quantum state representing the flow of the current. And we can go, of course, beyond 2 dimensions. We could have a state which is d-dimensional, associated with a finite dimensional vector, and that would be a discrete probability distribution. That is, for example, the excitation of the electron or numbers of the particles. That would be our states. And of course, we could have continuous probability distributions associated with properties and states that are infinite dimensional vectors, and those are the position of the particle, momentum, or the radiation. Let me also note here that most introductory courses in quantum mechanics, they actually start with the wave function of the position and the momentum, and they talk about those continuous probability distributions, and only at a later stage they discuss about probably spin, which is a lower dimensional state. Here I took the other path, starting from lower dimensions and building up to higher dimensions. I hope that made sense to all of you. And let me also briefly discuss about the interpretation of quantum state, because that is another issue that is quite interesting. It's rather controversial sometimes. A lot of people want to talk about the philosophy of quantum mechanics, what quantum mechanics means, because quantum mechanics is always associated with probability distributions and regarding measurement. And this is something that is not intuitive from a classical point of view. Let me mention that the reason why it is hard to interpret a quantum state is because it's really hard to interpret probability. And I want here to just draw an analogy between how we interpret probability and how those interpretations can move to have analogies to quantum mechanics. So the notion of probability can be defined in 2 different ways, broadly speaking. So we either have the frequentist approach, where the probability is just related to the relative frequency of a certain event in the limit of sufficient many trials. For example, we could have the toss of the coin. If we do that a lot of times and we collect some data and we do some statistics, then we can divide the times that end up in heads over the amount of times that we toss the coin, and that would be the probability that our coin end up in heads. On the other hand, we can define probability based on the ignorance that we have, the degree of confidence about a hypothesis based on some prior knowledge. Regarding the example with a coin, we can assume that the coin is fair, and based on that assumption, we can draw the conclusion that the probability of ending up having heads is 1/2. That is called the Bayesianism approach, because in probability theory, there is this Bayes theorem, that takes prior knowledge, prior probabilities, and gives posterior probabilities based on the knowledge. And I should mention that frequentist approach is more popular. Most probability theory textbooks start with the frequentist approach and then end up discussing the Bayesian approach. In quantum mechanics, we have slightly the reverse scenario, because there is one school of thought that a quantum state provides a complete description of an individual quantum system, that is close to Bayesianism in the sense that we have a quantum system and we have to assign some confidence on whether the state will be measured in one or another way. But we can also assume that a quantum state corresponds to a statistical ensemble of independent and identically prepared copies of a quantum system. This is called the ensemble interpretation. Is not as popular as the individual one. The ensemble interpretation was advocated by Max Born, by Einstein. The individual approach was mostly advocated by Bohr, Schrödinger, and Heisenberg. And the ensemble interpretation is a bit more agnostic in the sense that we first do the experiment a lot of times on a lot of identical copies of system, and then the coefficients in the superposition correspond just to those statistics. So we don't have the problem of interpreting, we don't have that much of a problem for interpreting those because that's what it ended up measuring. But for the individual approach, we have to go on a second level of interpretation to understand what exactly happened during the quantum measurements. And that's why I'm sure you have heard of the Copenhagen interpretation, which is by far the most popular in quantum textbooks. But there are other interpretations like pilot waves. This is also called the Bohmian mechanics. We have the many worlds interpretation. We have quantum Bayesianism. I will stop here. I will not continue talking about interpretation. I just want to give you an overview of how we can interpret quantum states in two broadly different ways. And do you have any questions regarding quantum states? I'll should pause here for a second. All right, I will move on. Let us also talk about the evolution. We already discussed about evolution in classical system and said that is deterministic. So in quantum system, the evolution is also deterministic. The only difference is that in classical system, we have differential equations for scalar values. In quantum systems, we have differential equations for matrices. The reason why I wanted to point that out, even though the two principles seem to be analogous and similar and the same, it's because there are a lot of misconceptions about quantum mechanics regarding determinism and indeterminism. I wanted to just make a remark that probabilities and indeterminism effectively is appearing in quantum mechanics only when we perform measurements. When the system is untouched, when the system is not observed, in total is a system that is autonomous. It just works deterministically. And if we describe this system in the phase space, those functions, the Wigner function will end up moving around the phase space, will probably change the shape. And if we consider as quantum states vectors, then the evolution will end up being a unitary transformation onto those states. Unitary matrices are matrices that satisfy this identity. And now there is a question, why did we pick that specific set? So if you remember, I mentioned that in quantum mechanics, we assume that the states are not just vectors, but are normalized vectors. So we want, during that transformation, the normalization to be preserved. And unitary matrices and transformations can do that, and that's why we pick those. This is a really broad way to describe evolution. And I also wanted to comment that this well-known Schrödinger equation is just a special case of it, meaning that if we have the unitary transformation be this exponential matrix, where the exponential part has the Hamiltonian, the time, and the Planck constant, then we end up with this differential equation, which is a Schrödinger equation. So the Schrödinger equation here is works only for continuous variables. So that's why I think it's preferable, especially for quantum information, to learn the evolution in terms of states that transform unitarily. Let us also see a specific example to see how evolution works, and that's also an example of how useful is Dirac notation in quantum information. Let us assume that we have this quantum state, which could be, for example, related to the polarization of a photon. Here we see a state that is more probable to end up being measured in the horizontal polarization. And let's assume that we apply this unitary matrix, this evolution, to our system. This is the first Pauli matrix, by the way, the matrix X, but written in the Dirac notation. And if we substitute that to the evolution that we described before, we end up having this expression. Now, expanding this expression, we end up having this series of vectors multiplied by some inner products. Some of them will vanish because 1 and 0 vectors are orthogonal to each other, and the other vectors will, since they're parallel, give an inner product equal to 1. So the outcome will be this state. So as we can see, this type of evolution to our quantum states has, as a result, the swapping of the coefficients. So now the quantum state is more probable to end up being measured in the vertical polarization rather than the horizontal. If you want to familiarize yourself with Dirac notation and quantum evolution and those calculations, you can probably try to see what would happen to these states if instead of the matrix X, we had applied the matrix Z or the matrix H. This is the Hadamard evolution, by the way. And maybe next week, we can talk about the results of those. And finally, let me also briefly get into quantum information and talk about how we can encode information onto quantum states. So in classical information theory, we encode information into bits. Bits are entities that can take up 2 different values, 0 or 1. They're binary. In quantum information, we encode information onto what we call quantum bits, or in short, qubits. Qubits are nothing but 2-dimensional quantum states, and before with measurement can be in this superposition, and after we perform the measurement, they collapse onto 0 or 1. So remember that since the self-interference exists before the measurement, the point here for quantum information is to keep the system coherent as much as possible, maybe mix up a lot of qubits and different operations, and at the end, perform different measurements in order to collapse the state in the 0 and 1. So practically at the end of the day, quantum information will be measured with bits, and we can encode information and decode it later on. In order to contrast the two and see how they're related, maybe it's a nice thing to represent a quantum state in the polar coordinates, and we end up having the quantum state as a point in what we call the Bloch sphere. Sometimes it's called Poincare sphere. This is a nice graphical representation of a qubit because it's just a point in a sphere. So whenever we have, for example, evolution of the quantum state, that would mean just a point going around the sphere. So quantum information can go anywhere in this sphere, but there are only 2 points that correspond to 0 and 1. So from that point of view, the bit is just a special case of the qubit. Now, next week we'll see how we can create situations where we have multiple qubits and how we can interfere them and measure them in such a way that we can transmit information and we can have protocols that go beyond what classical protocols can do. So we will talk about teleportation and we'll focus on the property that is responsible for the success of teleportation, called entanglement. We will define it and we will interpret it physically. We will contrast it to classical correlations and how entanglement can go beyond them. And we will conclude this course the week after by introducing noise into the system, see how the principles that we discussed today can be extended in order to take that into account. And the problem then would be to distribute entanglement in a noisy environment as further away as possible in order to do applications. Practically, we want to build up quantum networks. And we'll see that we can do that by using devices that we call quantum repeaters. You can find the slides on my personal webpage, and you can reach out to me at my personal email. And I also wanted to, before I conclude that, to give you some bibliography in case you want to learn more about it. Most of these textbooks are introductory. Probably Ballantyne's book is a bit more advanced, but I think that the textbook Entangled Systems by Aldrich is one of the best introductions to quantum systems, in case you want to check that out. And yeah, with that, I'd like to conclude, and I'm happy to take any questions. So I see a question of, so what happens if you have a pair of entangled photons? We'll definitely see that in the third lecture, and talk about when we have pairs of entangled photons, how we can swap entanglement and use it in order to distribute it further apart. We'll focus a lot on entanglement on the next lecture. So we can wait for that for a second, because in this lecture I didn't even define what entanglement is. So let's wait for that. And we have another question by Brahman. What does the word protocol mean in that usage? So protocol in quantum information is a series of operations that we can perform on quantum bits in order to have an input state and an output state. And depending on how we encode information on the input state, and then we decode it on the output state based on measurement, then we get information. So we can think of the word protocol in those quantum terms as if it's quantum operations for a certain problem that we have to solve. I see another question. Is it better to use a squeezed quantum state than coherent state for qubit encoding? So I didn't mention much about coherent continuous variable states regarding quantum encoding. I stick to qubits, which are the simplest. We can definitely encode information in continuous variable systems. Then we will encode information in the position and the momentum of the states. And that state can be anything, can be a coherent state, can be squeeze state. There is a different problem there on if we talk about those continuous variables, maybe it's better to think of it in the phase space and see how many of those states we can fit into the phase space. So sometimes it's better to have squeeze, sometimes it's better to have coherent states. There are even situations where we can use continuous variable states in such a way that we will end up having a qubit. You might have heard of CAT states or GKP states. So those are continuous variable states that behave as qubits. Brahman, you raised your hand. You want to have?
Yes, thank you. Just to follow up on the protocol question, from the perspective of networking, thank you for your very clear explanation, your extraordinarily clear introduction for those of us who are far away from physics. The word protocol means technical standards for the network. And so for the CQN this year, I'm looking at how internet designers in the course of their protocol development are thinking about quantum networks. What's going to happen with the language? In your world, we can't use the word protocol on those two. I mean, it has an abstract meaning that is the same, but we can't use it in the same way. Has there been any thought about that language issue, which is going to be important when the intellectual communities are coming together?
Thanks for the question. I think there is a slight difference between how the term protocol is used in physics and computer science. Next week, when I will introduce teleportation as the protocol, we see that it works in a sense as an algorithm because there are different steps that we take for a certain quantum state. So it's a protocol in that sense that there is an algorithm, that there are certain steps that if we take them, we always get the solution that we want to. But probably, yeah, I think at some point when more people from classical computer science move into the quantum world, there might be a need for a better terminology to differentiate those situations. I agree with that. Michael?
Thank you. I agree with what Sandra said. Your presentation was a very clear introduction to the mathematics of quantum physics. So that's great. My question is a little bit more on the philosophical side, something that is always interesting, the fact that to specify a qubit state, you need to specify two real numbers. In principle, that requires an infinite amount of precision to specify it exactly, to have a pure state. So you have a single point on a Bloch sphere. But to write down that number requires an infinite number of digits to specify real numbers. So in some sense, to create that state in the laboratory requires an infinite amount of information. But then when you hand it to somebody and they measure it, they get 1 bit. So what does that really say about quantum information encoding? Does that mean it's really inefficient? And if it's inefficient, then why do we get that quantum advantage in quantum computing?
Thanks for the question. I would even extend and make it even harder because it's not even, the coefficients are not even real numbers, they're actually complex numbers. And the idea here is that the way I see quantum states is through the ensemble interpretation, meaning that we have a quantum system in the laboratory, whatever that is, and we perform measurements on it. And after a lot of measurements on states on systems that we consider identical or identically prepared, then we will end up measuring those coefficients and we can define our state. Of course, the pure quantum states that I talked today are ideal. So it's the most ideal case where there's no noise. And as you mentioned, are states that somehow we can end up having infinite precision about what those coefficients are. But on the third lecture, when I will go into decoherence and talk about the noise, then we can see that when we have a quantum state as a density matrix, then we take into account imprecisions regarding measurements and problems regarding measurements of the state that might not end up being the state that we wanted to create. Because at the end of the day, every state is what we call a mixed state. Regarding the question about the encoding of information, it's a tricky question because a qubit at the end of the day will be equivalent to a bit because it's going to be 0 or 1. So it's not that quantum bits have more information than bits. It's more that qubits have this phenomenon, can exist in this self-interference phenomenon. So we take advantage of the self-interference and not the, it doesn't mean that the qubits have more information than bits. It means only that quantum systems have the ability to self-interfere. So we only take into account that phenomenon.
That makes sense. I also like your first answer was that you turn the question around and say how much information would be required to determine the state of an ensemble of particles. And that would take an infinite number of measurements on an infinite number of particles to specify the state by experiments. And that's what we call quantum state tomography.
Exactly.
So you're exactly right on that. Thank you.
Do we have any other questions? Great, we don't have any more questions. Let's see each other next week, same time, where we'll get into applications. For those who already know the quantum systems, maybe will be more interested to learning about the quantum information part of the course.
Thanks, Spyros.
Thank you, thank you. Thank you, everyone.
Bye.
Great. Thank you all. And just a quick reminder, tomorrow is World Quantum Day. And if you go to the website cqn-erc.org under events, we will be having an art entanglement talk with some of our partners in EU. Thank you all. Have a good afternoon.